I am Joshua Feinglass from the Active Perception Group at Arizona State University, and today I will be presenting our work towards addressing the misalignment of object proposal evaluation for vision language tasks by semantic grounding. We begin by asking the question, are all evaluation examples equally important? Here we consider importance to be the relevance of a data example from an upstream task, such as object detection, to a downstream task, which may utilize outputs from this upstream task, such as image captioning. The figure on the slide shows the decrease in performance for the combination of object proposals and a popular captioner as object proposals are removed. When using our annotation importance score, the captioner performance can be largely maintained when using only the top 55% of object annotations. This suggests the existence of a critical subset of object annotations, which are the primary contributors to increased performance on downstream tasks. From this observation, it follows that the inclusion of superfluous annotations in an upstream task can result in misalignment with downstream tasks. Misalignment means that higher scores on an upstream benchmark do not necessarily correspond to improved performance on downstream tasks. The likelihood of misalignment depends on how many superfluous annotations are included in the upstream benchmark. This principle is applicable to many areas, but in this work we choose to focus on object detection. To mitigate the effects of misalignment, we propose selecting critical objects using semantic grounding. An example of this process is shown in the figure on the slide. We first extract key concepts from the input captions, as shown in the top of the figure, which are given initial scores at the IC stage shown in the bottom left. These scores are distributed to the objects in the image based on their area at the I/O stage. Finally, the scores are propagated to adjacent objects using an inverse distance matrix and graph signal processing techniques to reduce sparsity, as shown at the IP stage. We perform numerous experiments in the paper, including both empirical studies and human studies, to validate the effectiveness and consistency of the method proposed here. The next figure shows an example of object selection for the visual genome dataset. The leftmost column shows the original annotations. The center column shows the annotations selected by our method when using an importance threshold of 0.075, and the rightmost column shows annotations provided by COCO. The plot below shows the increase in overlap between visual genome and COCO object annotations, as the importance threshold for object selection of visual genome annotations is increased. The results suggest that the method can actually identify the consistencies across different annotations performed by humans. Based on findings from earlier experiments, our last experiment proposes a benchmark specifically tailored to the design and comparison of vision language-oriented detectors. This benchmark includes a precision, recall, and F1 score, all of which we have shown to have high correlation with human judgment. We also include two different thresholds, a value of 0.075 to include a large amount of detail but filter out many of the irrelevant annotations, and a value of 0.30 to focus mainly on the most critical annotations. We hope that our method and proposed benchmark will be helpful in accelerating the design process for vision language detectors and identifying shortcomings of existing evaluation practices. Thank you for watching.